This is Lesson 2 in our Calculus 1 series, Important Functions to Know. We learned in Lesson 1 that functions are used to represent the relationship between quantities when one quantity depends on another. In this lesson, we learn about some important functions. The simplest is the linear function, so we start with that. Linear functions are of the form y equals mx plus b. Or to specify that it is a function, we might see f of x equals mx plus b, where m is the slope of the line and b is the y-intercept of the line. And this is the simplified form of a line, so we see this most often, and this is the slope-intercept form. We know that the slope m is change in y over change in x. That's the rate of change of y with respect to x. And so the slope of the line between points x1, y1 and x2, y2 is m equals y2 minus y1 over x2 minus x1. It's also useful to consider the point-slope form of the line. So the equation of the line through the point x1, y1 with slope m can be written as y minus y1 is equal to m times x minus x1. Now let's take a look at an example. The relationship between Fahrenheit and Celsius temperatures is given by a linear function. We know that the freezing point of water is 0 degrees Celsius or 32 degrees Fahrenheit, and the boiling point is 100 degrees Celsius or 212 degrees Fahrenheit. Find the linear equation for f as a function of c. F as a function of c. Normally we see y as a function of x. So just to get organized, I'm going to write down x is equal to c and y is equal to f, and that's going to help me organize my data. The points that were given here are 0, 32, and 100, 212. Again, we're using our Celsius temperatures as the x values and our Fahrenheit temperatures as the y values. Now that we have these 2 points that fit our line, we're going to need the slope of our line. So that's y2 minus y1 over x2 minus x1, and that simplifies to 9/5. Now notice we have the point 0, 32, so that tells us 32 is the y-intercept, or the f-intercept in this notation. So the equation of our line is y equals 9/5 x plus 32. Or in the f and c notation that they ask for, it's f equals 9/5 c plus 32. So in part B, it says find the Fahrenheit equivalent of 25 degrees Celsius. Okay, so we're plugging in 25 for c. Doing a little simplification here gives us 45 plus 32. That's 77 degrees Fahrenheit for f. And part C asks us to graph the function. So notice here that we have a slope of 9/5 and an intercept of 32. It would also be nice if we include on our graph the other point that we're given, 100, 212. So let's set up our axes to include those values. So here we have our intercept 0, 32, and here 100, 212. And so our line will look something like this. And this is f equals 9/5 c plus 32. Note here that the slope being 9/5 is saying for a 5-degree change in c, we expect a 9-degree change in f. For every 5-degree increase in Celsius, we get a 9-degree increase in Fahrenheit. Now let's take a look at power functions. Power functions are of the form f of x equals x to the a power, where a is a constant. We could also write this as y equals x to the a. Now, when a is n, a positive integer, we have these functions, for example, y equals x x squared, y equals x to the third, y equals x to the fourth, y equals x to the fifth, and so on. Now notice the difference between y equals x squared and y equals x to the fourth. The x to the fourth graph sits closer to the x-axis for x values near 0, and it goes up at a steeper rate here as compared to x squared. Same thing's happening with x to the fifth versus x to the third. The x to the fifth graph sits in closer to the x-axis. It has y values closer to 0 for x values near 0, and then also increases at a steeper rate. So comparing the even powers, we take a look at this graph. Here we see y equals x squared, x to the fourth, and x to the sixth on the same set of axes. You can see the comparison there. And here we have the odd power functions, y equals x, x to the third, x to the fifth, x to the seventh. And it's important to know the basic shape of all of these graphs as well as how they relate to one another. When we have a power function with a equals 1 over n, for n being a positive integer, we have y equals x to the 1 over n, or the nth root of x. We call that the nth root function. Our basic two that we see most often would be the square root of x and the cube root of x, so you definitely want to be familiar with these basic shapes. And it's also worth noting how these compare to the other even roots and odd roots. So here we have the square root of x, the fourth root of x, and the sixth root of x. And here we have the cube root, the fifth root, and the seventh root. Another two important power functions are y equals 1 over x and y equals 1 over x squared. You should definitely make yourself familiar with both of these graphs as well. Polynomial functions have the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to a1x plus a0, where n is a positive integer. So, for example, for n equals 1, let's compare the power function to the polynomial function. Here we have y equals x, and here, for example, is y equals 1/2 x plus 1. So this is our basic power function, and here we realize the slope can change and the intercept can change. Here's our basic parabola y equals x squared, and here, for example, is y equals x squared minus 2x plus 3. And we realize with the polynomial function, the vertex can change, and also we could see some vertical stretching if I had changed the coefficient of x squared. With an x to the third polynomial graph, we normally see this increasing and decreasing behavior. So it's important to recognize that something of this shape is likely a third-degree polynomial graph. A fourth-degree polynomial often has this W-shaped curve. Rational functions are of the form p of x over q of x, where p of x and q of x are both polynomials. I'm not going to suggest you memorize any of the shapes of these at this point, but we're going to learn later in the course how to sketch the graph of rational functions. Our important trig functions, y equals sine x, y equals cosine x, and y equals tangent x. I need to point out here, though, that it's very common to see students know the shape of the sine and cosine graphs, but not know the x and y coordinates of any particular points on the graph. So it's very important not just to know the shape, but to know that at pi over 2, the sine value is 1. At pi, the value is 0. At 3 pi over 2, the value is -1. At 2 pi, it's 0. So not only are you expected to know the shape of the curve, but you should be able to graph it in detail. Same thing with cosine x and with tangent x. So please make yourself very familiar with these graphs. So we've seen a collection of basic functions so far. Now we want to be able to take those basic functions and translate them about the plane. So for vertical and horizontal shifting, let's consider c to be a positive number. Then y equals f of x plus c is going to shift the graph of y equals f of x up c units. Y equals f of x minus c shifts the graph of y equals f of x down c units. If we have the plus c in with the x inside the function, that's going to shift the original graph left c units. And if we have x minus c inside the function, that'll shift the original graph right c units. For example, the black curve here is y equals x squared. That's our basic parabola. Let's take a look at the red one. That's x squared plus 3. So we're adding on the 3 after we take f of x. This is f of x plus 3. So that's going to be a shift up 3 units, because essentially what we're saying is take all the y values you had on your original graph and then add 3 to them. So that's going to shift the graph up. The next curve we want to look at is y equals x plus 3 quantity squared. This is saying take all your x values, add 3, and then square. So that's going to shift our graph left 3 units. So the black original graph is shifted here. And of course, we could have a combination of these transformations, something like y equals x minus 4 quantity squared minus 2. First thing we're going to do is recognize what happens closest to the x. Here we have an x minus 4 before it gets plugged into the function x squared. So we're going to move our original black graph over to the right 4 units. Then we're going to consider this minus 2, which takes all of those y values and subtracts 2 from them, leaving your vertex here and leaving us with the green parabola here. We could also talk about stretching and reflecting. And so for these guidelines, we're talking about c being greater than 1 now. Y equals c f of x stretches the graph of y equals f of x vertically by a factor of c. Y equals 1 over c f of x compresses it vertically by a factor of c. And then we have the opposite thing happening when we put the c inside the function. So y equals f of cx is going to be a compression horizontally by a factor of c. And y equals f of x over c is going to be a horizontal stretch by a factor of c. Putting a negative sign outside the function reflects y equals f of x through the x-axis, because this is saying take all of your original y values and now negate them. And here, if we negate the x, if we talk about y equals f of negative x, that's saying negate your x's and then compute the y. That reflects the original graph through the y-axis. So let's take a look at a few examples here. Here we have y equals sine x. And here we have y equals 2 sine x. The 2 is on the outside of f of x, and this is a vertical stretch by a factor of 2. Now let's put the 2 inside with the x. So it's going inside f of x now. This is f of 2x. So we have y equals sine x and y equals sine of 2x. This is a horizontal compression by a factor of 2. And if we put the 1 over c, the 1 over 2 inside the function, we're talking about a horizontal stretch by a factor of c. So here we have y equals sine x and y equals sine of x over 2. So the original sine function has a period of 2 pi. Now we're doing a horizontal stretch by a factor of 2. So the period of the stretched function is now multiplied by 2, and that's a period of 4 pi to get one cycle. Now, we could have a graph without any specific formula given for f of x and still talk about how to show translations, reflections, and stretching on the graph. So for example, let's take this original graph of y equals f of x. A reflection through the x-axis looks like this, and the formula would be y equals negative f of x. So whatever function we have here, now we're negating those function values, and our graph is reflected through the x-axis. Similarly, we start with the same function here, and we talk about y equals f of negative x. We're getting reflection through the y-axis. Now let's talk about combinations of functions. When combining functions by addition, subtraction, multiplication, or division, it's important to recognize the proper domain. So for y equals f of x plus g of x, f of x minus g of x, f of x times g of x, the domain is going to be the intersection of the domain of f and the domain of g. Because we need to make sure that whatever x value you're plugging into this function can be plugged into f and also can be plugged into g. So that's why we're looking for the intersection of these two sets. And it's very similar for the quotient f of x over g of x. We start with the intersection of those two domains, but we have to make sure here that g of x is not going to be 0. So we need to remove any x values here for which g of x would equal 0. So let's take a look at an example. F of x is equal to radical x minus 2, and g of x is equal to x over x minus 3. So let's consider h of x to be f of x plus g of x. Let's find its domain. Well, we know that this function is going to be radical x minus 2 plus x over x minus 3. That's how it's defined. Well, our domain here is going to be x minus 2 greater than or equal to 0. So that's x greater than or equal to 2. And our domain here is going to have x not equal to 3, so that our denominator is not equal to 0. So for this function, f of x plus g of x, our domain is going to be the intersection of these two sets, x greater than or equal to 2, but not equal to 3. So as I mentioned in lesson 1, when we're intersecting sets of real numbers, it's often easiest to visualize that on the real number line. So I like to draw out my sets here. X is greater than or equal to 2, but not equal to 3. And as an interval or a union of intervals, we can write that as the interval from 2 to 3, closed on 2, open on 3, union the interval from 3 to infinity, open on 3. And that's our domain for h of x. Now let's take a look at r of x, the quotient here, f of x over g of x. So we know that we're going to start with this intersection of sets, the same intersection of these two domains, but we also have to make sure that g of x is not going to be 0. So what x value makes g of x equal to 0? That would be x equals 0. So we start with this intersection of domains and then remove from it x equals 0. Well, it turns out in this case x equals 0 is not in that set, so it's still the same domain. But I want to make sure you realize here that x equals 3 is not in the domain of this function. So notice that when we did our quotient here, we simplified by multiplying by the reciprocal here. So we had radical x minus 2, and then we get multiplied by x minus 3 all over x. So it looks like this function here, we could plug in x equals 3. We would get 0. That would be fine. However, because this function came from the quotient f over g, we cannot have this defined for x equals 3. Because in fact, g is not defined for x equals 3. So x equals 3 is not in the domain of f over g. And it's important to note that. Now let's talk about compositions of functions. For functions f and g, the composition f of g of x is equal to f of g of x. F of g of x, we read that as. So essentially we're taking g and we're plugging it inside f. So for example, if f of x is radical x and g of x is x minus 3, what does f of g of x look like? F of g of x is f of x minus 3. So we're taking x minus 3 and putting it under the radical. So this is radical x minus 3. And g of f of x is g of radical x. So we're taking radical x and then subtracting 3. So this is radical x minus 3. And another example, g of x takes g and plugs it into itself. So we're taking g of x minus 3. So that's x minus 3 minus 3. So that simplifies to x minus 6. Now when we're talking about composing functions, we have to think about the domain of the composition. And the domain of f of g must have two important features. It must have x in the domain of g, because that's the first thing that we're plugging in here. X is going into g, and then that result goes into f. So we must have x in the domain of g, but we also must have g of x in the domain of f. So we must be able to take this result g of x and plug it into f. So in the example above, we have f of x equals radical x and g of x equals x minus 3. The domain of f is x greater than or equal to 0, and the domain of g is all reals. So for the domain of f of g, we must have x in the domain of g. So we start out with x in the domain of g, so x is in all reals. And then we need g of x in the domain of f. So we need g of x, x minus 3, to be in the domain of f, to be greater than or equal to 0. And so that says x must be greater than or equal to 3. And that's the domain of the composition function f of g. Another example, f of x is equal to x squared plus 2, g of x is equal to radical x. The domain of f is all reals. The domain of g is x greater than or equal to 0. Let's take a look at the composition f of g of x. This is f of radical x, so that's radical x quantity squared plus 2, and that simplifies to x plus 2. Now, when we look at this x plus 2, it looks like the domain should be all reals. But be careful, this function is a composition function, and we have to be sure that the x values we plug in here can first plug into g. G has a domain of x greater than or equal to 0. So we have to start with that as our domain. We need x greater than or equal to 0. We also have to be sure that g of x is in the domain of f. So we need to make sure that radical x is in the domain of f, but that domain was all reals, so that's fine. So our domain here of f of g of x is going to be x greater than or equal to 0. So again, don't be fooled by the final function. You have to consider the process that it took to get to this function. Because we're plugging g into f, we have to consider the domain of g first, and also consider that g of x is in the domain of f. Let's take a look at another. F of x is equal to 2 over x. G of x is 3x minus 6 over 2x plus 1. We see the domain of f is x not equal to 0. And the domain of g is x not equal to negative 1/2. The composition f of g has f of 3x minus 6 over 2x plus 1. So that means we're going to take 2 over this. And simplifying, we get 2 times 2x plus 1 over 3x minus 6. So again, don't be fooled by the final function. Let's consider the process. What do we need? We need x to be in the domain of g. So that means x cannot equal to negative 1/2. Also, we need g of x to be in the domain of f. So that means what comes out of here cannot equal 0. That's the domain of f. That tells us x cannot equal 2. So the domain for this composition is x is not equal to negative 1/2, also not equal to 2. So we can write that as a union of sets here. Negative infinity to negative 1/2, union negative 1/2 to 2, union 2 to infinity. All open sets. So moving forward with this course, we're going to expect that you know how to make some basic graphs, and that you know how to recognize some basic graphs. So please be sure to commit to memory all of the basic graphs you see in this lesson, as well as any we saw in Lesson 1. And this will conclude our lesson on important functions to know.